Hello everyone, this is Bukya Ravi Kumar and I'm going to explain about the topic that is X-ray photoelectron spectroscopy. We will be seeing many spectroscopies in industries and laboratories as well. So this is one of the spectroscopies that we will be seeing in many type of applications. So I'll be starting with contents. These are the contents I'll be explaining further in further slides. So we'll be starting with introduction, instrumentation, schematic, working principle, applications, advantages and limitations. So we'll be starting with the introduction. So basically X-ray photoelectron spectroscopy is a powerful analysis technique that provides detailed information about the elemental composition, chemical states, and electronic structures of a material. It works by irradiating a sample with X-rays, causing core level electrons to be ejected, so that is knocked out, and measuring their kinetic energies to determine the binding energies. So XPS is highly surface sensitive, analyzing the top 5 to 10 nanometers of a sample and offers quantitative insights into elemental concentrations and chemical states, so such as oxidation or bonding environment. This non-destructive techniques is widely used in fields like material science, thin film analysis, and surface chemistry to study metal, polymers, ceramics, and many more. So next slide is it's a extractive information about the introduction which I have explained before. So X-ray photoelectron spectroscopy. So XPS is known as X-ray photoelectron spectroscopy, which usually works based on the photoelectric effect. So I'll be explaining what is photoelectric effect as well. So this X-ray photoelectron spectroscopy can identify the elemental composition of the sample, so which analyzes the sample to a depth of 5 to 10 nanometers. So basically this XPS spectroscopy analyzes the sample to a depth of 5 to 10 nanometers. XPS is a powerful measurement technique because it not only shows what elements are present but also what other elements they are bonded to. So this is something unique about this XPS spectroscopy. So this is the instrumentation of XPS. So these are the following components of the experimentation of the XPS spectroscopy, that is X-ray source. Typically aluminum K alpha or magnesium K alpha anodes will be using. So electron analyzer. So this will be measures the kinetic energy of the emitted electrons, and there will be a detector records the count of electrons and the energy of the electrons. Also we are requiring, or our requirement will be vacuum uh, operates in ultra high vacuum to prevent electron scattering. So as I said before, I'll be explaining photoelectric effect. What happens here is, so here you can see a X-ray tube through which the X-rays will be uh, traveling towards a sample. So these X-rays will be being incident on this sample, and here you can see the arrow that is coming towards this electrons. So when it gets incident on this, it will penetrate into the orbits, and the electrons, core electrons of this, will be knocked out or ejected from the shell that is being present in. And so here you can see that one electron is knocked out of the this sample. So this is the knocked electron is called as the photoelectron. So the X-rays that is being incident on this, if it's holding the maximum energy or the energy is high enough so that the when it gets incident on this will be knocked out. So the knocked electrons are called as photoelectrons. So this is what happens in this X-ray photoelectron spectroscopy. So this is a schematic diagram of X-ray photoelectron spectroscopy. So here you can see the X-ray tube, So and a sample holder which is for the placing of sample material. Also a electron energy analyzer, electron detector as well, and XPS spectra. So here I have explained before that what is photoelectric effect. So through which the X-rays will be being incident on the sample. Here you can see in the diagram. So this is a working principle of XPS. X-ray photoelectron spectroscopy works by directing X-ray onto the material surface, causing the ejection of electrons from the atoms. So as I said before that, so the directing X-rays will be incident on the material surface and causing ejection of electrons from the atoms. The energy of the emitted electrons is measured, and using the known energy of the X-rays and the kinetic energy of the electrons, the binding energy of the electrons is calculated. So when the electrons are being ejected out, so those will be captured and will be providing and will be detecting through the computing system their kinetic energies, and by that the binding energy of those electrons will be calculated. So this binding energy is unique to each element and its chemical state, allowing XPS to identify and quantify the element present on the material surface, as well as provide information about their chemical environments. So this technique is highly surface sensitive, so typically analyzing the top 1 to 10 nanometers of the material. So this is the output which we get from the computing system. So here you can see count of electrons and kinetic energy graph. So that we'll be getting from the output analysis. So here you can see the increasing of kinetic energy, and here you can see the two equations. H nu is equals to bending energy plus kinetic energy plus work function. So bending energy will be calculated by the kinetic energies. So here you can see that if the kinetic energy is increased, then the bending energy will be decreased. So vice versa happens. So by this we can calculate the bending energy as well. And here you can see the bending energy graph as well. So which is a combination of count of electrons and bending energy. Here you can see it is decreasing. So these are the significance that I have mentioned before the equations. H nu, which is known for energy of incident photons. So B is binding energy, K is kinetic energy. So phi is working function. So working function is nothing but energy required to knock the electrons from the atom. So from the above graphical analysis, we can identify the element present on the sample surface by comparing their binding energy with already known data. So basically this XPS is used to measure elemental compositions of the surface top 0 to 10 nanometers usually. Empirical formula of pure materials, elements that contaminate a surface, chemical or electronic state of each element in the surface, uniformity of elemental composition across the top surface. So these are some other applications which is basically used routine and somewhat less routine. So we'll be starting with XPS is routinely used to analyze inorganic substance, metal alloys, polymers, elements, catalysts, glasses, ceramics, paints, papers, inks, wood, plant trees, makeup, teeth bones, medical implants, biomaterials, coatings, viscous oils, glues, ion modified materials, and many others. So now, somewhat less routinely, XPS is used to analyze the hydrated form of materials such as hydrogels and biological samples by freezing them in their hydrated state in an ultra pure environment. So these are some advantages by using XPS spectroscopy. So I'll be starting with the first point, non-destructive. provides both elemental and chemical state information. So this is high surface sensitivity. So as I said before many times that it will be calculating, or it will to a depth of 1 to 10 nanometers of a sample, non-destructive. The technique is generally non-destructive, preserving the sample for further analysis. So wide applicability is one of the best advantages of this XPS. Works with a variety of materials including metals, polymers, ceramics and semiconductors. So also these are some limitations for the usage of XPS spectroscopy. So this is basically requires ultra high vacuum, limited depth analysis, only detects elements heavier than the helium, surface sensitivity analyzes only the top 1 to 10. So more than that it's very, so it unable to detect and provides the spectra. So limiting its use for the bulk material analysis. So these are the information. I hope you liked it. So thank you.